Hello. In this module, I'm going to be giving an overview of current and projected climate change impacts to forests in southern New England. I am part of a team of climate adaptation specialists and researchers at the Northern Institute of Applied Climate Science. NIACS is a collaborative, multi-institutional partnership led by the Forest Service and includes federal, forest sector, conservation, academic, and tribal organizations to address scientific and management needs in the fields of climate and carbon. We provide practical information, resources, and technical assistance related to forests and climate change. Much of our work tends to center on helping natural resource managers make climate-informed decisions, and we work across the upper Midwest and Northeast primarily. The work of NIACS supports the Northern Forest Climate Hub, one of a network of centers that delivers science-based, region-specific information and technologies to natural resource managers to support climate-informed decision-making in forested and non-forested ecosystem management, conservation, and stewardship. Our hub's core focus areas are the forests of the Midwest and Northeast regions. There are 10 regional USDA climate hubs across the country that focus on agriculture and ecosystem management. You can go to our website for more information. This presentation will help you better understand current and future projected changes in temperature, precipitation, snow cover, and stream flow across the region, how climate change is expected to impact forest ecosystems, including vegetation, soils, hydrology, wildlife, and disturbances in southern New England, how climate change can compound other stressors, including forest pests and pathogens in the region, as well as site factors that influence a forest's vulnerability to climate change. When talking about climate change, it's often tempting to drift into conversations about the interesting weather we're having. However, climate requires long-term horizons, a minimum of 30 years. That's enough time to have a meaningful average that's not swayed by year-to-year variation and stochasticity. Basically, anything shorter than weeks, years, even decades, those time scales are driven by unpredictability and randomness. We can see this in this illustration. The dog is all over the place, totally random, following its nose, and that's essentially what the weather is doing. On the other hand, the walker is generally on a pathway that is more moderate and steadier over the long term. The walker represents the climate pattern that is not getting caught up in what the dog or the weather is doing. Similarly, when we talk about climate trends, we're looking at that long time scale, decades to centuries. We can think about this longer climate trend in southern New England. First, looking at changes in average annual temperature. We see that changes in Massachusetts and Connecticut have risen almost 3.5 degrees Fahrenheit since the start of the 20th century. In Rhode Island, this change has been about 4 degrees Fahrenheit. We see that the 10 coldest years on record have been 1940 and before, and the 10 warmest years have all been in the 1990s and later. We can also use climate models to understand future temperature changes. This shows not only how annual temperatures have already increased that 3.5 degrees in southern New England, but it also shows that annual temperatures in the region are projected to increase at least 2 degrees higher than the historical average under low emission scenarios, or under high emission scenarios, temperatures may increase up to 10 degrees hotter than the hottest year on record by the start of next century. We know that these changes in climate, including temperature, are not expected to be the same in every season. For example, we expect that winters will warm more than other seasons under low emission scenarios. And we see increased warming in winter, as well as summer and fall under high emission scenarios. And it's not just the temperature that is changing. There are many changes to our climate, including more extreme rainfall, sea level rise, coastal flooding, as well as warmer winters and a longer growing season. And these all are causing substantial disruptions to the world around us, including our forest ecosystems. We know that total annual precipitation has increased about 4.5 inches in the region over the past century. In Massachusetts and Rhode Island, the wettest consecutive 5-year period on record was 2005 to 2009. Looking at rainfall events across the Northeast, we really see how the increased precipitation that we are seeing annually is coming more often in these larger events, bringing more rain over shorter periods of time. Fluctuations between these events really shows that variability is an important piece to the trends we are seeing. We see more variable rainfall, more rainfall overall, and all coming in these larger events, typically. For example, in 2010, intense rainstorms led to extensive flooding throughout southern New England. And during 2005 to 2014, Massachusetts and Rhode Island experienced the largest number of 2-inch extreme precipitation events, which is about 30% higher than the long-term average. We also recall more recent heavy rain events that have affected our ecosystems more recently. However, extreme droughts are still occurring sporadically. For example, Massachusetts experienced extreme drought during 2016 to 17 and again in 2020, straining water supplies. So we can see the impacts of drought that happen during the dips of these heavy rainfall event peaks as well. We see increases in annual rainfall projected for the Northeast, with 4 to 6 inches or 6 to 8 inches more rainfall projected annually, depending on if we're looking at the low emission scenarios or high emission scenario. And these patterns vary seasonally, again, with wetter winter, spring, and little change or possibly drier summer and fall under high emission scenarios. In terms of sea level rise, since 1900, global average sea level has risen about 7 to 8 inches. Between 1930 and 2020, the region has had an average rate of sea level rise equivalent to about 11 inches over a century. Global average sea level is projected to rise another 1 to 4 feet or more by 2100 as a result of both past and future emissions from human activities. This will be accompanied by large increases in tidal flood events, with impacts including coastal erosion, flooding, and impacts to coastal ecosystems, including marshes, forests, and estuaries. We are also seeing these trends in warming winters, including decreases in snowfall, cover, and depth, particularly in December and January. With the decrease in snowpack, we expect to have increased and more unpredictable freeze-thaw cycles, including later freeze and earlier thaw, as well as sporadic warm-ups throughout the winter season, overall resulting in less time with frozen ground consistently. This figure here shows areas with snow cover for at least a month historically, outlined in red, and under a high emission scenario in white in New England. These impacts could increase soil disturbances, leading to soil carbon losses and erosion, and impact the ability to carry out harvest operations that need frozen ground, particularly sensitive sites. In addition to less snow, we expect to see an increase in precipitation in the winter, including more extreme rain events and rain on snow events or rare rain on bare ground. Some of the shifts in temperature and precipitation are speeding up the hydrologic cycle, causing earlier peak stream flows in the spring, which we can see here on the map. All of these can result in erosion from rain on snow or bare ground and damage to infrastructure and aquatic habitats from these events. The flip side of warmer winters is a longer growing season, and we can see this in shifts in plant hardiness zones. In southern New England, the USDA plant hardiness zone is projected to shift from zones 5 to 7 across the region to zones 7 through 9 by the end of the century under high emission scenarios. These projections equate to 3 to 7 more weeks to the growing season added. We can see this in the figure, which shows mid-century projections for the change in date of the last spring freeze and first fall freeze under low and high emission scenarios, as well as these projected for the end of the century. With these longer growing seasons, we do have the relative benefit of more time for plant growth and photosynthesis. However, there may also be drawbacks, as we may see evidence of phenological shifts in different plants and animal species, which may lead to phenological mismatches, such as early bud break leading to frost damage, or the loss of cold hardening. It may also benefit pests or non-native species that have a competitive advantage of earlier leaf out or flowering than native species. Longer growing seasons can also lead to moisture stress and drier conditions during the growing season, even given the increased precipitation in the region. If we think about the water cycle in the forest, water comes in through precipitation and generally is absorbed to recharge the groundwater or leaves the system as runoff. In the case of that earlier spring snowmelt discussed earlier, and increased runoff during extreme rain events, this means that more water is potentially lost from the system. Warming temperatures can also drive water loss from soils and vegetation through transpiration, leading to some drier conditions. These combined impacts put ecosystems at a higher risk of drought stress especially if they are already on droughty sites with shallow soils, south-facing ridges, or are communities of more mesic tree species that are already not in their optimal growing conditions. Though drought is less common in the Northeast, it may become more common with climate change in future emission scenarios. In summary, some of the points made before, this is because longer growing seasons will lead to more moisture losses from transpiration, from plants, and evaporation from the soil. A larger share of total rainfall will be delivered in large events, which aren't as effective at recharging soil moisture. Projections indicate that we will experience longer stretches between rainfall events in the future. And warmer springs mean that snowmelt happens earlier in the year, shifting hydrologic cycle and soil moisture regimes. Wildfire may become more of a management consideration in a significant way as well. This model predicts future changes in wildfire risk based on mean maximum air temperature, mean annual precipitation, and elevation. By the end of the century, we may see 50 to 100% increase in fire risk or probability in the region under future climate scenarios. This may be true especially with projections of warmer and drier summers, tree mortality from less suitable conditions leading to more fuel loading, and shifts towards fire-associated species. However, wildfire risk may not change as much if we see more spring and summer moisture, regeneration of mesic species over fire-adapted species, more land fragmentation, and increasing trends of human fire suppression. Other events besides wildfire, including heavy rain, Heat waves, drought, windstorms, and hurricanes may also become more frequent or severe. Though we've seen these more in the past decade, it's still difficult to model the future occurrence of these stochastic events, though we know that they are occurring more frequently and doing more damage, and so we can expect that increased frequency and severity in the future. We also expect that with climate change, there will be increased damage from forest insects and diseases. Part of this is due to indirect impacts. Stress from other impacts like drought, moisture stress, may increase tree host susceptibility to insect damage. Also, direct effects include that insects may be able to migrate more north with warmer winters and speed up their life cycles, allowing them to reproduce and spread faster with fewer lethal winter temperatures. Some of these insects and diseases of specific concern in southern New England are emerald ash borer, beech bark disease and beech leaf disease, hemlock willy adelgid, and spongy moth. Some of these are impacted by warmer temperatures like hemlock willy adelgid, but for some, their impact is more indirect, as other climate change impacts may compound to make host species more susceptible to insect and disease damage and make these diseases or insects more damaging and causing more mortality because of that. We also know that invasive species are and will become even more of a concern. Warming temperatures and longer growing seasons might help populations expand and become more competitive over native species in our forests. Deer herbivory will also be a more widespread concern, as populations may be able to grow and thrive better in warmer conditions and with milder winters. We expect to see these impacts more towards the northern edge of their range. Years ago, the Department of Defense characterized climate change as a threat multiplier for national and international security. This term is equally applicable when we think about ecosystems. Forests are already facing many threats, independent of and influenced by climate change. Stressors and the interactions among them make all the difference and can compound to make consequences for species and ecosystems worse. This is also exemplified for the disease decline spiral. If we think about how individual trees exposed to these compounding stressors may be more likely to see declines in their health and eventually die at faster rates because of these compounding factors. With these climate change impacts in mind, we can also think about what this might mean for changes in tree species composition that are projected to occur in our forests in the next century. Tree species habitat is based on a number of factors, including temperature, precipitation, elevation, latitude, soils, slope, and aspect. Since many of these factors are predicted to shift with climate change, the Landscape Change Research Group with the Forest Service Northern Research Station has modeled projected changes in tree species habitat using a number of these factors. Here we can see projected changes in habitat for tree species in Rhode Island using the Climate Change Tree Atlas results from the Climate Change Research Group. In this summary table of Atlas models, first we have the change class 45 and 85 columns with the potential changes in habitat by the end of the century based on low and high emission scenarios. Next listed is the species' current abundance based on FIA data and its adaptability rating or its ability to withstand disturbances based on species traits. These three elements are combined to come up with the overall predicted capability of the species to persist on the landscape under low and high emission scenarios. Here is a summary of projections of tree species capability for common species in New England from the Climate Change Tree Atlas. We want to keep in mind that when we think about projections of habitat change, this can look like multiple things. For example, 50% reduction in habitat could look like the density of species in the current range is reduced by 50%, or it could look like that habitat range shrinks to only the best areas in that species coverage, original coverage across the landscape. In general, when we think about these projected changes in forest composition, we know these changes will occur slowly over time, and that mature and established trees should fare better than younger trees, regeneration, and trees on marginal sites. It's important to consider factors that will influence these changes, including but not limited to competition, management actions, and disturbance. In summary, here is the list of the major climate change impacts discussed from the New England and New York Forest Ecosystem Vulnerability Assessment that are predicted to affect our region. You can find this report and other regional climate vulnerability information at forestadaptation.org/New England. We can think about these regional climate change impacts and use them to assess climate vulnerability of our forests on a local site-specific scale. Vulnerability is the degree to which a system is susceptible to and unable to cope with adverse effects of climate change, including climate variability and extremes. It's important when assessing climate change vulnerability that natural resource managers take these broad regional climate change trends and information that I just presented and use your knowledge and expertise to bring these trends down to the site level that you're working on, taking into account the site's specific hydrology, elevation, past management and disturbance history, soils, location on the landscape, etc. Vulnerability is the combination of potential impacts and adaptive capacity. This means that when we assess vulnerability of our site, we need to think about first, the potential impacts of climate change on the site, both indirect and direct effects. So these are things like the temperature change that we expect to experience at the site. Will it potentially be moderated by a proximity to a body of water or being at higher elevation? You might also consider what stressors are likely to affect the area or how key species are expected to respond to climate change. And then the other side of this equation is the adaptive capacity of the site. So here we are thinking about the ability of our system to cope with change, which may be bolstered by species tolerance to disturbance, high species diversity, or other characteristics at the site that provide multiple pathways of recovery to disturbance. For example, high landscape connectivity at your site could provide multiple pathways for the system to respond to disturbance through species migrating to more ideal areas as conditions change. One tool that landowners or natural resource managers can use to think about assessing climate change impacts at the site level is the Keep Forests Healthy Landowner Scorecard developed by the Nature Conservancy, Cornell, and NIAX. You can walk through items like this on the scorecard to understand how the characteristics of your site might exacerbate or buffer potential climate change impacts. For example, looking at soils. If you see obvious soil erosion, rutting, or frequent flooding, your climate risk might be higher versus if you see no evidence of soil erosion, rutting, or severe flooding on your site. As another example, take invasive species. If you have multiple invasive plant populations present that cover extensive areas of your site, You might be at higher climate risk than a site that has no invasive plant populations present and none close by. Take another example of moisture stress and drought. You might have a site where species on site are not drought tolerant or soils are sandy or prone to drought. And this would make your site more at risk, especially in terms of moisture stress and drought in terms of climate change. This is a useful tool to help us get into the mindset of thinking about how the physical and ecological characteristics of your site can modify impacts from climate change. This can help you to prioritize what climate impacts might be the most challenging for you at your site and what you need to address to meet your management goals moving forward. The Oak Resiliency Assessment Tool is another useful tool to assess climate impacts that was made specifically for oak forests focused on southern New England. The assessment walks through helping you identify potential impacts and adaptive capacity at your site to better understand and rank the overall vulnerability of a particular stand. The combined consideration of the impacts and adaptive capacity helps us understand whether the site has multiple ways it could respond to disturbance without management intervention, or if it's very vulnerable um, and may decline in health and function if certain impacts were to compound with each other and may require management intervention to improve forest health and functioning. Thank you for listening. For additional information, please refer to the resources listed here and in the description below.